Hi, today I'm going to talk about electromagnetic suspension and its application today. We know that opposite poles of a magnet attract and the same poles repel. This is basic principle behind electromagnetic propulsion. But electromagnets have the ability to create magnetic field through electric current, which means that a magnetic field can be controlled. It can be either on or off. Electromagnets can be easily made by connecting the ends of a copper wire to positive and negative ends of a battery cell. This will create a small magnetic field. This idea of creating magnetic field with wire and battery is applied to design a maglev train wheel system. The system contains three components. The first one is a large electrical power source. Second one is metal coils lining a guideway or a track. And the third one is a large guidance magnets attached to the underside of the train. The difference between a conventional train and maglev train wheel system is that the maglev doesn't have an engine. Instead of using an electrical motor or conventional engine, the maglev uses a magnetic field created by electrified coils in the guide walls and the track combined to propel the train. To explain the system more in depth, the magnets used in the system are superconducting. Superconducting magnets are electromagnets that are cooled down to extreme temperatures during use, which dramatically increase the power of the magnetic field, which means that when they are cooled down to negative 450 degrees Fahrenheit, they can generate magnetic fields up to 10 times stronger than an ordinary magnet. These magnetic fields interact with simple metallic loops set into the concrete walls of the maglev guideway. The loops are made of conductive materials like aluminium, and when magnetic field moves past, it creates an electric current that generates another magnetic field. Three types of loops are set into the guideway at specific intervals to do three important tasks. One creates a field that makes the train hover about 5 inches above the guideway. A second keeps the train stable horizontally. Both loops use magnetic repulsion to keep the train car in the optimal spot. The further it gets from the center of the guideway or closer to the bottom, the more magnetic resistance pushes it back on track. The third set of loops is a propulsion system run by alternating current power. Here, both magnetic attraction and repulsion are used to move the train car along the guideway. Imagine the box with 4 magnets, one on each corner. The front corners have magnets with north poles facing out, and the back corners have magnets with south poles outwards. Electrifying propulsion's loops generates magnetic fields that both pull the train forward from the front and push it forward from behind. This floating magnet design creates a smooth trip, even though the train can travel up to 375 miles per hour. A rider experiences less turbulence than a traditional steel wheel trains because the only source of friction is air. Another big benefit of the maglev is safety. Maglev trains are driven by the powered guideways. So any two trains traveling the same route cannot catch up and crash into one another because they are all being powered to move at the same speed. Similarly, traditional train derailments that occur because of cornering too quickly can happen with maglev. The further a maglev train gets out from its normal position between the guide walls, the stronger the magnetic force pushing it back into place becomes. So that's all for today. Thank you for listening.